Welcome to my talk. I will give a talk about JavaScript cryptography and some cryptographic concepts with some code examples in JavaScript. I will talk about hashes, HMAC, derivation, encrypting, passwords, symmetric chiffres, digital signatures, and many things like this. And I will just mention this because it's a broad topic. It's a topic that could cost you at least 1 year in your life to study this in details. But I believe that after this talk you will be more confident when to use which cipher, how to use it, to differentiate between MAC and, for example, other things like signatures, to understand that AES encryption is not just a function like SHA-256, which takes something to encrypt it and a password. It's very, very much more complicated, and developers should know it. And developers should also know which ciphers are bad, which are broken, which are not good, and what is the difference between the RSA and elliptic curves and many, many, many other this. And developers should also be aware when they use JavaScript that cryptography in the browser might be something which can cause security problems. So, just a few words about me. Most people know me here in Sofia because I'm well-known software engineer, entrepreneur with several startups, and I'm most famous by training people to code, developers. I'm author of 15 books, yes. After the last one, which I'll show you a bit later, it's 15. I was involved in blockchain development and training in the last year, but today I'm switching into expanding the SoftUni internationally. So I will work on Arabic language, on Spanish, on Portuguese, and then many others. So I'm deeply involved in training. I run maybe the 3 of the most successful training academies for software engineers and digital skills in Bulgaria, starting from the National Academy from Software Development, which was acquired by Telerik Academy, where I spent 4 years, and I trained tens of thousands of software engineers who work here in the software industry now. And not all of them graduated successfully, but most of them started a job. It was interesting that people don't come to me to study, they come for a job. And if they can bypass studying, they will be happy. But it doesn't work in most cases. So I'm very proud of SoftUni, where we train hundreds of thousands of software engineers and digital skill experts, and of course not all of them graduate. That's why it's still hard to find developers in Sofia. My goal was to solve this problem, but it's unsolvable because the people in the input, are not enough. People who want to study software engineering and who want to put enough effort to learn this are not enough. So there is no solution. Until the brain injection hardware is invented, still it's not ready. So what I'm doing now, in the last few months, I broke my leg, so I stay at home and I write a book about cryptography. It's entirely in English, and it's highly devoted to developers, and this is the inspiration for this talk. I highly recommend this because it's maybe the first book which is well systemized, well organized, and it's for developers. It's not about mathematics. Yes, it should be mentioned. Yes, you should know what is elliptic curve and what are the domain parameters of elliptic curves, but it's for developers, and it's about code. Most things I illustrate in Python. It covers many things, but you can find it on internet, or you just write Nakov cryptography or CryptoBook Nakov, and you'll find it. Contributions are welcome in GitHub because it's open source project and will be published freely. And yeah, this is my inspiration to give a talk because I work a lot to teach people that encryption is not just invoking a function which does something as a black box. This is a bad idea, and people who encrypt data and work with security this way are just losers, and they will be hacked sooner or later. But I will talk today about hashes, HMAC codes, key derivation functions, how to encrypt passwords the right way, not hashing passwords, like many developers will answer at interviews. Well, not putting plain text passwords in the database, which is the biggest anti-pattern in the software industry. And because people use the same password at many places, and it becomes interesting when you have one of their passwords. I will explain why the AES encryption, the most used standard, it's not just something which takes a password and text and returns encrypted text. It's about key derivation functions like Scrypt or Argon 2. It's about block modes like counter mode or go up counter mode. It's about initial vector, which should be crypto-random, about the MAC authentication code, which ensures that after decryption, you will know whether the password was correct or not for this description. And finally, I will talk about digital signatures, and I believe that these things are the minimal thing that a developer should know, and should know at least at this level, which I present here, to call himself developer. Otherwise, it's just a wannabe developer. Or at least senior developers should know this very well and should differentiate between RSA and elliptic curves digital signature algorithm, and should know that elliptic curves use curve, and some curves are weak and some curves are strong, and that 256 key curve-based 256-bit key curve gives 128 bits of security because of the RHO algorithm. But I don't have time for all of this. If you have a few weeks or just few days, you can pass through the book. Finally, I will talk about why at the client side in the web browser, cryptography may be victim of many attacks, and it's not easy to protect yourself, and guarantees are not given to anyone. For example, if you work on a blockchain project and you handle crypto wallets which keep thousands of crypto money, it's not a good idea to bypass the security attention in your app. And still, it might be hacked. For example, if someone hack your server and just change the JavaScript code which does the encryption, just without replacing the random generator with some predictable randoms, and they will be happy with all the keys from all your customers. This is the problem, and this is a deep problem, but we are developers. If we work with money, with finance, we should be careful. So, what is cryptography? Most of you know, so I'll pass fastly here. Cryptography, it's about security, it's about data protection, it's about encryption, it's about storing data in a secure way that guarantees that people who are intended to read the data will be able to read it, and the others should not be able to read it. And many attacks are here, and many ways to protect are here. So it's about encryption, decryption, it's about hashing, a one-way function which transforms some text into some hash, like, for example, Git uses. About message authentication codes, about key derivation functions which derive a key from a password, about key agreements, algorithms and skips like elliptic curve, Diffie-Hellman key agreement, and many others which are executed every day without you knowing about it. For example, if you open a website, it's typically HTTPS. First, the HTTPS downloads the server certificates, validated. It's a X.509 certificate. It verifies some signature with elliptic curves or with RSA signature algorithm. Later, the SSL algorithm establishes a mutual secret key between the server and the client. This is called the key agreement or key exchange. It's based typically on Diffie-Hellman, some kind of function, typically with some elliptic elliptic curve cryptography, and then they use AES, but AES is a bit many other things. Typically, SSL uses the EES counter GCM mode, which is a kind of authenticated encryption, which guarantees that encrypted data is encrypted correctly. It's also authenticated that people who are intercepting the traffic cannot change the encrypted data without being caught to do this. So cryptography is everywhere. It's usually hidden, but it's really everywhere. If you connect to your Wi-Fi, another set of encryption schemes are established, and many algorithms are used together. Cryptography algorithms are not used alone. So we talk about encryption schemes or key derivation schemes because they are sequences of one algorithm chained to another, to another, to another, to another, and this is what I will show you. Finally, I'll show you digital signatures, signing and verification of signatures. So let's start from the JavaScript and how developers may start. Usually, people in the industry use libraries, use some already packages coded by strong people who understand what they're doing. And crypto libraries in JavaScript are somehow, how to say, there is no single source of do everything library. There is no good library which is capable to do all the things I will explain you today. In Java or in C#, there is a bouncy castle or other big, very strong hundreds of thousands of lines of codes which implement everything. But in JavaScript, it's a set of small libraries. Some of them are fast, some of them are not, some of them are buggy. I will show you a bug in the, for example, the elliptic curves digital signature algorithm library, which I fixed and made a pull request, but the author told that people who rely on the bug will be unhappy, so he will not fix it, and I agree, yeah, because the fix and making the library working correctly will break the people who rely on the bug, and this is normal. This is the way software works. So crypto is the Node.js crypto library. It's just a wrapper around the OpenSSL. You may know OpenSSL is the most used cryptographic library in the world. It's built in web servers, in SSH, and many others. In the SSL implementation, but it's server-side only. It's not pure JavaScript, it's just binding, and it's C and C++ code behind. Crypto.js works well with hashes and HMACs. It doesn't support all modern hashes. Argon 2 is very interesting library, which I highly recommend for hashing passwords, and I will show you how to do this. AES is AES implementation, AES-JS. I prefer this library because it doesn't do a lot of magic. You construct the encryption scheme yourself, and because there are some, let's say, better libraries who just take text and password and encrypt, but this is a bad idea because you don't know what's inside. For example, in the EBC mode of AES, the security is not good. And many other things can be wrong in the AES encryption. For example, using a non-random initial vector. This allows you to decrypt the traffic later. Many other things. And finally, the elliptic is a very well designed and written library for elliptic curve cryptography. It implements the classical signature algorithms over elliptic curves like ECDSA and EdDSA, as well as elliptic curve Diffie-Hellman over the most used in the industry curves, which are SECP256K1. There is a bug here, and ED25519. Wow, it's hard to pronounce this, especially in English. So, very shortly, I'll pass through hash functions because I believe most of you have already used hashes. For example, if you make a Git commit, and I believe all of you have done at least one commit in Git in their life here, otherwise you will be not in this lab, in this seminar. So it's a hash. The version, each version Git creates, it's a hash, and it's broken hash. And Git use SHA-1, which is proven broken, and there is online tool which can generate fake hashes. But Git still uses this, and they have written a special protection behind this, and when they find a collision in the Git commits, they say, oh, you're doing bad things, I will suspend your account. Because this is guaranteed to be attacked. By mistake, you cannot generate collision in the SHA-1, but you can. So what is hashing about? It's when you have a text message or binary message or file or document, you pass it through a cryptographic hash function which produces a digest. The digest has certain length, for example, 256 bits or 512 bits, and it's irreversible. So there is no algorithm which can reverse back the hash to the original text. Sometimes this is possible, for example, through a dictionary. If you make a dictionary of text hash, and do backwards, but in the general case, you cannot. So if you have the hash of some password, for example, you cannot recover the password. It's impossible. So it's a one-way function which is infeasible to invert, but this is by design. There are broken hash functions who are not behaving like this. For example, in MD5. Producing MD5 collisions or reverting MD5 hashes is something like a classical broken algorithm, and there are online tools who do this with ease. So it's extremely little chance to find a collision. For example, for the SHA-256 hash function, it's proven that the chance to find collision is less than a meteorite hits the Earth and destroyed several times in a series. So that's why people believe that hashes uniquely identify something. For example, in Git, if you commit a set of files, the hash guarantees that you have unique commit ID, and this ID will never collide with some other commit. This is, by design, wrong assumption, but this is how Git works. And yes, there are collisions, real, for SHA-1. So let's review a bit these functions. SHA-2 is a modern hash function, which is described in RFC, is the most used, and there are no collisions today found. The first who will find collision by chance or by some research, cryptanalysis, will become famous. So this is an example. The hash is shown as hex. It's 64 hex digits, which is 32 bytes, which is 256 bits. It's used in Bitcoin, in IPFS, and in many a lot of softwares. SHA-3 is recommended. It has better security. For example, it doesn't suffer from the length extension attack. I don't have time to explain it, but it's better hash function, and I highly recommend to use either SHA-3 or Blake2S or some modern and later hash function. It's more secure, but it does the very similar job. It's almost the same like API and like what you can expect. It's used in the Ethereum blockchain, for example, and in many other apps. Blake2 was one of the finalists, and this Ketchak SHA-3 was the winner, but these were the second choice, and it's faster than the others a little bit. And does the same job, and it's highly secure. It works well, and it's very, very good function. It has many variants, etc. RIPE-MD 160, it's considered weak, but it's still not broken. There are nobody knows a collision about this. Let's tell what is a collision. A collision are two different texts, which after hashing give the same hash value. For example, hello and Svetlin. If both are hashed to the same value, this will be called collision. And collision are bad because you can, for example, fake a commit passed in the few days ago and change it, for example. They will cause Git to break. Git will not work if you have collisions. It will give you error. You will say git push, and it will say, oh, something's broken. I cannot push. Please change something in your commits there. Yes, this will happen if you try to push. Or otherwise, you will overwrite the changes of someone else in the past. And you will be highly unhappy. Or the other guy will be highly unhappy, of course. So RIPEMD is still unbroken. This is the way Bitcoin generates his addresses. So it's very interesting that if two people open a wallet on the Bitcoin blockchain, by chance, they can have the same address. And the chance to this to happen is 1 divided by 2 raised to the power of 160. So it's not extremely complex to find the collision, and there are found collisions for this. But this is a long story. So don't use 160 bits. This is not secure as of today. Use big hashes, at least 256 bits. So, wow, the example here is bad. And there are broken hash algorithms, so you should forget about them, but you should remember about them, because if you find them, you should warn the people that they should change. For example, MD5 is easy to find collisions. SHA1, there are collision generator which fakes PDF signatures online. You can play with it, and many others. I don't have enough time, and I already mentioned that GitHub has collisions in the commits because it uses SHA1, and they are in a period of transition. Maybe 1 year later they will fix this and will move on to some modern hash. They are redesigning something. Oh, let's put some code. Let's have some code. So in JavaScript, you know, we most often use some kind of NPM packages, like, for example, this Crypto.js, which is documented here. It, of course, doesn't have a documentation, like many things in JavaScript and in the industry as well. The documentation is just few examples, and for example, they mention that they have this. So you can open the code and learn yourself how to use it. But the open source is good because it's the best documentation possible, but it's not user-friendly. So how to use this? Just require and say, please calculate this hash of some string. This might be string or might be some array or buffer, which is the binary sequence of binary data in JavaScript. This returns buffer or some kind of binary data, and when you call to string, it's transformed to hex value. So the result is something like this. HMAC 256 it's a variant of SHA3. But some people believe that in SHA3 there are some constants, some just magic numbers inside in the source code. So people believe that there might be a kind of crypto backdoor inside. So they changed these values and created another hash which behaves similarly, which is called HMAC 256. Yes, this is the story of Ethereum blockchain. For example, Vitalik, you know him maybe, did this change because he is afraid of hidden backdoors. And there is some special science of building backdoors. For example, in the elliptic curves, it's possible, and it was proven that NSA was injected a backdoor in some of the official crypto standards about random number generators, and they paid 10 millions to make this standard the default implementation to be the broken backdoor algorithms. So people believe a lot about this because this once happened. So, RIPEMD is another example and another example. I will not run it, or I can run it because it will be just one click, but I need to find the correct window. So hashes run like this, nothing interesting. They are usually fast, and you can use them to identify documents. But if you identify documents, please use large hashes. It's not a good idea to use SHA1 because someday people find collisions and break your software. So another story is about HMAC, message authentication codes, key derivation, password functions, and others like Scrypt and Argon too. Many people believe that when they hash their password, it's protected. It's not. I will prove you why. But first start with the HMAC. What is HMAC? It's hash-based message authentication code. It's a kind of hash which combines an input value, input data, with some secret key. So it's a kind of combination between encryption and hash. So the easiest way to do this is to hash the message with the key together. You just combine them in like a string concatenation and hash them together. And this is proven unsafe, so don't do it. Use some MAC algorithm, like HMAC, like Hmap, like CMAC, and others. So this is an example how calculated, and this is the accordingly calculated result. This is called HMAC SHA-256 because HMAC combines a hash function with some other security construction and makes a message authentication call. I will show you whether to use it because it's not obvious. Why do we need MAC codes? It's not obvious. I will show you later in this topic. So the next thing is key derivation. People believe that when they encrypt something, a password is used. It's wrong assumption. Encryption chiffers don't use passwords. They use keys, and these keys are of fixed size. For example, the AES cipher uses either 128 bits of key or 256. It depends on the block size of the cipher because most ciphers are block size, and it depends on a few other parameters. So people believe that the easiest way to derive a key from a password is just to hash the password. And it's true. This works, but it's not secure. I'll explain you why. First, people who know that it's not secure have created this PBKey df2 password-based key derivation function 2, which is described by our internet standard RFC 2898. And how it works, you request some kind of key size, how many bits you want to take from the password. You explain how many iterations you need, and you define some kind of hash. So how does it work? It's it hashes the password, takes the output, combines the hash with the password, and next hashes again. And the output is combined with the password again and hashed again, and this is done 1,000 times. Why do you want to do this 1,000 times? It's a waste of resources. You use your CPU, which you pay for in the cloud, right? But you need this because you want to make password cracking hard job. You don't want someone to try 10 million password candidates per second. So the easiest way to crack a password is just to generate ABC, ABCD, 5 times A, and generate the possible passwords and to check whether they are valid or not, right? This is in the movies they are doing like this. So I have done this successfully on Windows NT, for example, in the past. But it's no longer possible with the modern systems. It was possible in the past. Currently, this algorithm protects you from fast password cracking. Password cracking is still possible, but it's not fast. And if you put too much iteration, for example, 1 million, your login will take 10 seconds or 1 minute. So it's a matter of to find the right value for you, that your system is not very slow, it's acceptable at speed, but the crackers who can eventually obtain your password hash to be unable to revert it. Because what protects the encrypted files, for example, encrypted PDF, encrypted Excel file, encrypted Word document, it's not the encryption algorithm, it's the key derivation function. The key derivation function, which transforms your password to an encryption key, it holds the protection against brute force attacks. This is important to know. And that's why the parameters inside here are good. And of course, do you know that graphic processors like GPUs, your gamer's card, or Bitcoin miner, or some kind of miner, Bitcoin miner in the past, can perform thousands of parallel computations like this. So this was good idea, this function, because before the crypto mining. Today, it's unsafe. And it should not be used, of course. So you should use better key derivation functions like Scrypt, like Argon 2, and because they are ASIC resistant to especially designed hardware like Antminer, which is used to mine bitcoins today, and many others like GPU cards, which gamers use to play games. And it uses a lot of iterations and a lot of memory. It can be configured to use, for example, 128 gigabytes of RAM just to derive the key. If you don't have this RAM, it will be very slow. But the GPU card does not have this RAM, or at least does not have many threads which can use this amount of RAM in concurrent execution. So the Scrypt standard is the first or popular which solves this problem. It's ASIC resistant and FPGA. This is a specialized hardware which can be programmed to do something on a low level, and it's highly efficient. For example, ASIC can be 1 million times faster than normal hardware. So you may know that there are ASIC for Scrypt. Yes, it's true, but it depends on these parameters. These parameters define how many iterations you need and how many, what is the block size, and this, when you multiply this, you can find how many RAM you need. So ASICs are believed to be unable to have a lot of RAM. There is no ASIC today with 1 gigabyte of RAM. So if you want to make the cracking of passwords hard job, use this. For example, if you encrypt nuclear codes, please use good encryption with good key derivation parameters. Everything of this is hidden. For example, if you encrypt Excel file in Microsoft Excel, this is done internally, but it's hidden. And also, Scrypt is not the best thing. This is an example how to do Scrypt. It works with something called salt. This salt should be randomly generated, because by design, when you derive a key, when you encrypt a document, you generate a random salt. You derive the key using this password and the salt, and you keep this salt along with the encrypted document. So this means that if I save 2 times an Excel document with the same password, I will obtain totally different document. This protects from dictionary attacks. You cannot, because you can make a dictionary. This encrypted document corresponds to this password. If you have millions of documents, you can recover passwords by a dictionary attack. So salting prevents from dictionary attacks in the general case. And salt is usually 128 bits for all algorithms, because most security standards today protect for 128 level of security. Let's show you the example of this Scrypt. How does it work? It just, it's asynchronous and it derives the key. If I make this bigger, the number of iterations, it will be slower. Wow, it should be power of 2. Okay, let's say then something like this. See, it needs more time now, because it's a lot of iterations. So if you encrypt your hard disk or some secret files, it's a good idea to use big values here. And if you encrypt interactive login for a system with 1 million users, it's not a good idea, because it will just hang. Okay, so Argon 2. Argon 2 is better function than Scrypt. It's built later. It's the winner of competition about building this such encryption functions. It's highly reliable. It has similar parameters like memory cost, like this is the variant of the algorithm. I recommend Argon 2GI, which is resistant to timing attacks and many others. It has better security, and it has time cost and many things, and it always explains, you always tell how much long key you need. For example, if you perform 128-bit encryption, you will need 16 bytes. If you perform 256 bits encryption, you will need 32 bytes. So this is how it works, and this is what is the result. The result is just very similar like Scrypt. But in Argon, it's also designed for password verification. So see the first result here. It's just a key derived. So you generate a random salt. Here you pass this salt. It's not a good idea. It's just an example. Don't pass the same salt, because the same salt from the same password will always generate the same hash. If you have the same hash, you can build a dictionary, right? And it's vulnerable to dictionary attacks. So it's better to use a random hash, and by default, if you just hash a password without nothing else or with some settings, it will build something like this. People who have worked with web servers know this. This is hold an encrypted passwords. It holds together with the first line. It's one line, it's just the space is not enough. So it says the algorithm is Argon. These are the parameters of algorithms. My salt is this one. This is the salt until the dollar mark. And this is the hash. So if I encrypt the password again, it will give me different salt, which is random, and different hash. This is how modern passwords are protected. This is not the only way, but this is a good security way to protect passwords. And this is how most frameworks do it internally. For example, the Laravel framework in PHP does exactly this internally, without asking you, of course. Because these people know what they are doing. So let's talk a little bit about password encryption. Password encryption is something where people who write apps do every day. For example, login and register. You know this. Username, password. Login, register. So the stupid way to implement this is clear text password. Just keep the top password exactly in of the web server. This is very, very, very bad idea, because someone will take the database, for example, your boss, he will see your password and will log in your email, because stupid people use the same passwords at many places. And not only stupid, some people just don't know that this is not a good idea, because then they didn't consider this. So, and it's hard to remember 1,000 passwords, because I have registration at 1,000 sites. So people just say, click save in the browser, and Google have it for passwords, of course. They claim not, but they have it. Okay, so simple hashing, just SHA from the password, it's not a good idea, because the password cracking will be fast, and also there are dictionary attacks. What I mean by dictionary attacks, you download 10 gigabytes compressed file. It holds 1 billion possible passwords along with their hashes. So if you want to find if your password is, for example, Paris or London, very simple, stupid password, you just scan through the right column of this 1 billion password dictionary, and you find the correct one. Yes, it might happen that your password is not in the dictionary, but once someone cracks the Yahoo passwords, for example, they will add them to the dictionary, right? So hackers constantly take possible passwords by backdooring some servers. For example, the login can be intercepted. So if the server is hacked, there is no protection which can save you from someone to take your password. Okay, you can hash the password client-side and send the hash, but this is not usually done. People believe that SSL and HTTPS are strong enough and that servers are not hacked, which is not true, and that's how it works. So never use the same password, especially for important websites, or use at least two-factor authentication with SMS, like GitHub does, for example. So salted hashed passwords, it's something like get the password, get the random salt, and HMAC them, and store the obtained result together with the random salt in the database. In the past, this was considered very secure, but it's not, because it's GPU crackable. GPUs are multi-processors in one chip. They have many processing lines which run together. So they can crack, for example, 100,000 together, passwords together. And get the other 100,000, so it's very, very fast. So it's not ASIC resistant, so use ASIC resistant KDF password hash. This is the state of the art, the recommended today. Yeah, someday we'll have maybe other attacks and other algorithms. This is how it evolves. So Argon 2 is the good maybe solution, but depends on the settings. Argon 2 may be easy to crack, maybe hard to crack, depends on the settings. So how to use Argon 2 in JavaScript? Just install it from npm and require it and use this one. This installation involves some C++ code compilation, so it's fast, it's optimized, and runs very well. It's important that your implementation of Argon is the fastest possible. Why it's important? Because password crackers, if they have faster than your hardware, they will have advantage, right? If they have faster than your algorithm, they will have advantage. You don't want to give them advantage. For example, if you implement this 1,000 times slower than the normal speed, than the state-of-the-art speed, password crackers will implement Argon 2 hashing faster than you and will crack faster than you verify passwords at all. So this is how it works, and if you want to register a user, you just configure Argon, for example like this. You hash the password and you put this one in database. It's safe. It's very hard to crack this. If I give you this, it will take months or years to crack this. And if my password is good enough, for example, 20 characters, it will be practically impossible to get the password out from this. This is the recommended way to do it. And verification is like this. You take the hash from the database and you call the verify function from Argon. It parses this string, it builds Argon with these parameters, etc., etc., etc. This is an example how to do. Okay, this is this one. So if I try to verify with password, first I encrypt password and get some hash, and I verify with correct and incorrect password, and I obtain true or false. This is what we expect. So the next thing here I will talk about is symmetric encryption. Symmetric encryption is believed by some people to be just a function which takes password and text and produces some cipher. At high level, this is true, but there are a lot of things which can break or make this insecure. So instead of just relying on some library, it's better to control what you're doing. So there are AES chiffers or other chiffers like Serpent, like RC6, RC5, and there are two modes, authenticated and not authenticated encryption. In not authenticated encryption, you will never know whether the password is correct or not and whether the decryption is successful or not. So symmetric key chiffers use the same key for encryption and decryption, and usually this key is derived from a password by Argon 2 or Scrypt or other key derivation function. Popular algorithms are AES, ChaCha20. This is very modern and it's very, very fast and highly secure. It's designed by Daniel Bernstein, the author of QML, of the EdDSA cryptography, and many others. But there are a lot of broken algorithms like DES. DES, it's broken, don't use it. The triple DES was an attempt to fix this, which is again broken. And RC2. These are 64 bytes chiffers, and they were state-of-the-art when the machine had 64 kilobytes of RAM, but today it's different. So it was designed for the previous era. It's not modern. So there are stream chiffers and block chiffers. Block chiffers just take up a block of 128 bits, encrypt them by some key, and return a result. A stream cipher can stream something. For example, stream encrypted video, for example. And they can pass DLO seeking. For example, if you have 16 gigabyte of video file, which is encrypted, stream chiffers will be able to seek with this encrypted data. And this is, usually chiffers are block chiffers, and they are converted to stream chiffers. Block chiffers usually split the data into blocks, which have the same size, for example, 128 bits. Then encrypt each block, change the internal state, and encrypt the other blocks. Sometimes they use padding because the last block will don't have the right side, the correct size. Sometimes they use other transformations, like the CTR block mode. So block chiffers can be transformed to stream chiffers, and we usually use stream chiffers by using a block mode of operations. And now, not all possible block modes of operation are secure. Some block modes are not secure. So with some work and with some cryptanalysis, you can decrypt the AES traffic, for example, for ECB mode. I don't have time to explain this well, but use CTR or GCM block of mode of operation, or just use ChaCha20 Poly 1307 chiffre, which is the most recommended. Google currently use this for, unless you change it by default. So the AES chiffre, also known as Rindel, this is a person from Netherlands with this hard to pronounce name. It works in blocks of this size, 128 bits, and it works together with some kind of block mode. There are still, it's old chiffre, very old. It's maybe 20 years ago, like from its invention, it's still unbroken, so it's very good. This is good news. 20 years, nobody can break this, even quantum computers also. So modern CPUs implement this as a hardware instruction, so it's very fast, which is good because you don't want to lose time in your cloud because you pay per computation, right? It will cost you money. So AES instructions in your CPU make the AES very fast. And not only very fast, they have other applications. So AES is used by most web browsers today. So if you, for example, when you open a website, it uses internally AES with symmetric chiffre, but it also uses the so-called authenticated encryption to ensure that if someone intercepts the data between you, for example, your internet provider, he will be unable to change anything after the key negotiation, because the key negotiation is bound to the certificate, and it will be impossible for man-in-the-middle attacks. But this is a complex to be explained. If someone can explain SSL and TLS in 5 or 10 minutes, he will be absolutely very strange how to do it. It's very complicated. It's about key agreement, about digital certificates and server identities and many other things. So the block chiffres encrypt some block by block. First block, second block, third block, it has a state and changes the state. Initially, it starts from the so-called initial vector. This is the initial state of the chiffre, which combined with the encryption key is used to encrypt the first block. Then this initial vector is transformed from the internal state is just changed, and the next block comes. Otherwise, if you have the same data in different blocks, you don't want this to be encrypted the same way, right? If you have, for example, the letter A 1 million times, if the chiffre is not good, it will have repeated patterns in the output, which is not good. It's leak of information. So use CTR or Galois counter mode. This is the better way, but it's not implemented by the most libraries because it's new. It's maybe something like 5 years ago invented. And use random sort, because otherwise some kind of attacks will be possible. For example, some kind of dictionary attacks over the blocks, because they may have dictionary and they can try to reconstruct the internal state of the AES chiffre from the output and from many other things. It's complex to explain. Some modes use padding algorithms. It's preferable to avoid this because padding just changes the size of the input with some additional letters just to have the correct block size, and it's just more complex. Okay, so usually we use password derivation because we don't have keys people use passwords. They don't use keys because it's not easy to remember 64 hex digits. Most people can't remember this. So they use passwords, and keys are devised. And usually some kind of authentication is added to the cipher. So the output from the AES algorithm usually holds a special value which is a kind of hash which is created from the key, from the encryption key and from the input message, which cannot reveal some kind of information because it's hash and it cannot be returned back to its original, but it guarantees that when you decipher the text, you will know whether the password was correct or not. It will be authenticated. You will be sure that the person who created the message and the person who decrypted the message have the same original message. This is called authenticated encryption. And for example, wireless networks always use authenticated encryption because otherwise your Wi-Fi router can replace some network packets with some data and change something, right? And this will not be detected unless you use authenticated encryption. So it's by default mostly. For example, AES GCM cipher uses authenticated encryption. So how does it work? You have a password, you derive a key from it. For example, using Argon 2, like I showed you. Later, you take the input message, you take the key, and you invoke the AES algorithm. It produces several things: the cipher text, the encrypted data, the initial vector, which is the randomness used at the start for the AES cipher. The first block is XORed with this initial vector, which is random, and it produces the MAC. In more details, the input message, together with the random initial vector, together with the key, passes through the AES encrypt method and returns cipher text. Later, finally, this is the salt is generated here. And finally, the input message plus the key, plus the derived key from the password, passes through the MAC algorithm and generate message authentication code to know whether your decryption password was correct or not, and whether after decryption the message decrypted matches the original message before the encryption. So how it works? So the animations are broken. At the decryption, it works totally at the opposite side. So first, the key is derived from the password. Later, when you have the cipher text, the initial vector for this AES cipher, the key for decryption, the secret key, you can recover the original message. Once you recover the original message, you check the MAC code and find whether it was correct or not. So how to use this in the browser? You will find many magic AES libraries and don't use them because you don't have control and you don't know what is inside. Yes, I know you are developers, you want to have password, text, and output. Yes, it's better, but you don't know what's inside. And you absolutely, this is unpredictable. It's not a good idea. So it's better to control this. You can write this, of course you can write this in your own code, but you have the source code and you will not know what's inside. So I will use the AES.js together with Argon 2 for the key derivation, together with the crypto for secure random numbers. This is the OpenSSL crypto random generator, which is bound to the entropy generator from the operating system. Some operating systems don't have entropy, so you don't have work. There are, for example, embedded controllers which don't have enough functionality, they don't have true randomness. The Linux kernel driver, for example, locks things like the network packets, the keyboard, the mouse, and many others, and collects the so-called entropy, the source of randomness. And when you call, please generate a random number, it's really unpredictable. And there are many attacks, for example, stolen bitcoins, because of broken random generator. That's why it's truly important for cryptography. And Crypto.js I will use for hashes. So how it starts? First I derive the key. This is something we have already seen in the past slides. I will upload the slides. Don't need to I will put them on my blog together with the video from this talk. Later what we do is just to generate the salt, the initial vector. Later we initialize the CTR mode of operation, this counter. We initialize this with the initial vector. This should be random, otherwise the security is less. It does not, how to say, it's not guaranteed that your message will be decrypted, but security is reduced if you don't use a random number here. So AES always come with initial vectors. The block chiffers always come with this initial vector. This just returns bytes, the encrypted bytes. But the output is not just this. Later we calculate the MAC. It comes from the plaintext together with the, where is it? With the key. The plaintext with the encryption key, which is derived from the password, together are hashed by this HMAC to create the message authentication. And the output is this. It's better just to run the example because the slide is too small to have it. I will post also this code, of course, at GIST, and you will see what happens. The interesting thing is that what it holds. Usually, when you encrypt something, for example, crypto wallet, you don't know what's inside. You are given just a binary file. For example, when you encrypt an Excel, it's binary, it's unreadable, you don't know what's inside. But here we know. So this is the encrypted message. This is how it looks like. It says, I use Argon 2. This Argon 2 is sorted by this random value. If you use this, together with the password, you can derive the key. Once you have the key, I will use AES-256 counter mode cipher. This cipher will be initialized with random initial vector. This will always be changes, this and this, and of course these two, because they depend on the first. And this is the encrypted data. It has the same site like the input message, which is also a way to leak information. Because you will know how many letters your password is, right? For example, if this is a password. So what you can do, just append some random string. For example, if this is a XML, it will be pretty easy. Or if this is a binary data, you should design some kind of padding algorithm and depadding after that. But you should know that encrypting data leaks the input message length or size. And this is the cipher text and the MAC. When we decrypt this, we do the opposite process. So how it works, I will show you here. First, we have the password. From the password, we calculate the encryption key. I also printed, see, this key at the encryption and decryption comes from the same password with the same salt, and it's the same key. Next, what I do is just to initialize the AES counter, I take the initial vector from the encrypted message. For example, if I have Excel file, the Excel file will hold this random initial vector. It will hold the salt. It doesn't hold just the cipher. People believe that it holds only the encrypted text. No, it holds the encrypted text with many other random ticks which are used together during the decryption process. And this is how it works. It's hidden from you, but this is how it works. So I decrypt it, and finally I calculate the MAC and just throw an exception if the MAC doesn't match. And in this example, finally I try to decrypt with wrong password, and this is the output. I don't have enough time, so I will pass through the digital signature, which is the last topic here. So what are digital signatures? Signing some messages like signing documents. You put your signature, which is some calculation. You add this signature to the message. And this is the way, for example, when you send money with your e-banking, you have a signature. You sign a transaction. I sign that I pay to the electro provider my bill for the electricity, for example. And you have signature, digital signature, which is generated from your private key, which is derived from username and password, or it's somewhere else. So digital signature provides authentication, which means that the signed message holds a proof that some holder of some certain public key has done this signature. If you don't have the private key, you cannot have this signature correctly. It holds integrity, which means that after signing, I cannot modify it. For example, if I sign that I pay 1,000 level to Peter, the bank cannot take this signature and say 50 level. It cannot be changed after signing. like at the notary. So non-repudiation means that if I sign the message, I cannot say later, oh, it's not my signature. No, it's permanent. You cannot revoke signing something. If you sign it, it's forever. And so digital signature are based on public key cryptography, or the so-called asymmetric cryptography. So messages are signed by something called private key, and private keys has corresponding public keys. So they are always come together in a pair. In the elliptic curve cryptography, which is an example for public key crypto system, the public key can be generated from the private key, and this is how it works. In RSA, for example, the traditional digital certificates for your web server typically use RSA. The keys are generated together through some special mathematical properties, but let's stop here. So signatures are verified by the public key. If you want to see that someone have signed a message, you need his public key. But you don't know who is this person. This is not identity system. It's not identity. Identity is your personal passport. So it connects your photo with your public key. This is nothing to do with identity. You know that someone who has the private key corresponding to this public key is the author of this message. So your bank, when you sign your contract for payments for online banking, they send you a public key, and they ask you for your passport, for your identity card, and they put in their database that this identity card with your national number, etc., matches this public key. Or this is guaranteed by digital certificates. I don't have time to talk about digital certificates. So digital signatures can use different algorithms. RSA, which is based on discrete algorithms and just prime integers to be easier, or elliptic curve algorithms, which are the modern algorithms. They use shorter keys and have better cryptography strength for the same length. More precisely, you can encrypt with the public key and decrypt with the private key, which is not exactly like this. It's more complicated because you need to have a combination of algorithms, and you can sign with the private key and verify it through the public key. So the RSA is based on discrete algorithms, on the hardness of the discrete algorithm problem, and elliptic curve cryptography relies on the elliptic curve discrete algorithm problem, which means that you can multiply a point on the elliptic curve by integer, but the opposite operation is not possible. It's hard to explain. You can find it in the book. So it's proven mathematically that the same cryptography level of security or strength is for this size of RSA key, and 256 is elliptic curve cryptography key. In fact, the number of operations that you need to perform to break this cipher is the key size by 2. It means that a curve which holds a private key with 256 bits can be broken in 2 of power of 128 operations. You should be aware of this, and quantum algorithms will slightly change this. Well, it will be possible, by theory at least, to break elliptic curves. So blockchains use this. Why? Because they have signed transactions which are publicly in the chain. They should be short. The signature should be short. That's why elliptic curve cryptography is recommended there. It's a big dispute whether to use large RSA keys or ECC, but RSA is slower, it's proven. If you generate, for example, 60 kilobytes RSA key, it will take maybe half a minute on laptop. So let's talk about elliptic. In JavaScript, you use elliptic. When you, this is the library I can recommend. It has optimization, it's fast, and it uses curve. It's a big story about the curves. There are many curves. Some curves are less secure than others. Some curves are completely broken. They have backdoor, which means that NSA have a secret key, and they can decrypt your, they can find your private key by their key. It's proven. We have example of this. But usually you generate a key pair,
but usually if you have the private key, you can generate the public key. The opposite is impossible. It's infeasible, to be precise. So key can be compressed, which means that the public key is 256 bits on this curve. On other curves it might be different. And when it's the public key, the private is this of this size, and the public is this size, twice, because it's point. It's x and y coordinate on the curve. The curve is just some graph, some function on the two-dimensional space. So when it's compressed, it can fit in this number of bits. This is how it works. I will demonstrate you the ECDSA. Here, when I run it, it generates for me random key. This is the private key. This is the public key. It's twice as long. And this is the compressed public key. This 023 or 03 compresses the y coordinate because it's math. You don't need this. So the next thing to do is just to sign. How to sign? Generate the key pairs, make a message hash. ECDSA doesn't sign messages. It signs hashes, which should be the size of the curve. For example, for 256-bit curve, the message to be signed should be the same length, the same number of bits. You sign it and you obtain something like this. This is the signature. One number, another number. In fact, this is a random point on the elliptic curve, which is generated by some algorithm, and this is a computation which involves your private key and this random point, and this is the key recovery. This say, if you have this 0 or 1, you can recover the public key. Elliptic curves DSA algorithm can recover the public key of the signer out from the message and from the signature. So this is how you verify the signature. It's very easy. You put the message hash, the signature, and the public key of the person who claims to have produced this signature, and it returns true or false. So here the first case will have true, and here we'll have false because we generate a new key pair. I just illustrate that with wrong key, the signature verification will fail. And finally, I show you how to recover. This is the book in the library I found, because all the keys in this library I taken as hexadecimal. But in this SE recover, it should be decimal. And it's not very easy to convert it. It's a bug. But if you patch it, this code will stop working. But this is the way you can recover the private key. So how does it work on the Bitcoin blockchain, for example? Bitcoin transactions are signed messages on the chain. For example, Peter, some address sends 5 Bitcoins to some other address. If you take the signature together with the signed message, you derive the public key. From this public key, you can derive the address of the signer because it's just a hashing. The Bitcoin address is a kind of hash of the public key. And this is how it works. Finally, I want to show you its EdDSA. This is an optimized similar algorithm, but different. It works on the so-called Edwards curves. It's complex to explain. But if you use this curve, it's faster, and the keys fit into 256 bits. In fact, the private key here is 252 bits. In fact, it's less secure, let's say, but it does the same thing, and I will show you the demo here. This is the recommended scheme, the recommended, way to do it. The private key is 256 bits. The public key is also 256 bits, which is better than the other algorithm for the same security strength. And the signature is this. And the signature, in this algorithm, you cannot recover the private key, because the first is based on, or the EOGAMO signature scheme, and this is based on Schnorr signature scheme, which is totally different kind of mathematics behind. It looks similar, yes, similar for developers, but it's different. So, in short, prefer this signature for most modern applications because they are faster, they are slightly better as a security, and This is the way, for example, OpenSSL and many modern crypto libraries work. So yeah, that's maybe enough. And finally, the client-side security. It's a problem because your browser can be hacked. For example, if you generate a Bitcoin wallet in your browser, if your browser is hacked, everything is broken. Of course, if your server is hacked, it can also lead to the same thing. But for example, if your server is Amazon, it's unlikely that Amazon get hacked. It's less likely than your server, for example. So there are many in the browser attacks. You just install something, it patches your browser, and you're ready. What they usually do, they just patch your random generator, and it's no longer random. So the keys you generate are predictable, and hackers, without having any other information, can decrypt everything you have. Cross-site scripting is another thing. If you have cross-site scripting, someone could inject a JavaScript, and when he injects a JavaScript, he can modify your cryptography, right? Your code. So broken code, modified code can compromise the security. So if you use in the browser, never generate random numbers yourself, like R&D function or what was it? It's insecure, it's predictable. Use this web crypto API. People who designed this crypto API and to implement it know what they are doing and know how to protect it. For example, you cannot change the prototype of the random generator function because you can change the toString function for object, right? In JavaScript, it's possible. So the same way, someone could change the random generated function, but here you cannot. Many protections like CORS, like code signing, signed JavaScripts, some script which verifies the other script. Many complex things can be invented, but please keep your server secure. If you have some wallets and many other things, just put them on separate server, not together with the others. Control the people who have access to the source code. For example, once a lot of crypto money was stolen this way. They hacked one from the core developers. This developer have pushed backdoor from his account. They pushed a backdoor in the crypto implementation of the cryptocurrency. And later then they used this backdoor to drain the wallets. So this is how you can be hacked. This is how Amazon also can be hacked, but they care about this. So please be cautious, and I hope this was interesting, and I hope that most of you no longer believe that AES is like hashes, password and something can produce encryption. And questions, do we have time? Wow, I talk too fast. Okay, I'll be around and I'll be happy to answer your questions. I'll be there, and because I want to give space to the next speaker. And so, thank you.